bad news. I'm not ready for that test. We're gonna move that test back to Friday, Monday. So I know you guys are glad to hear that?
Yeah.
Alright. We will slow down, reteach some stuff. We have some homework to go over. I've had some people asking really good questions that are really beneficial to the people around them. The only problem is there were 2 people in the room. And then during advisory period today, I had some really good questions asked that benefited maybe 3 people. So I know some of you are scared to ask questions in front of the class, but I think we have a lot of questions to answer. So if we can, let's talk. Just talk. Does anyone have any questions on what they want to see? Because essentially, we're supposed to be reviewing today, correct? For our test tomorrow. So we have that chapter 5 quiz. Maybe let's look at the chapter 5 quiz and answer any questions we have on that, and then move on. Is your question chapter 5 or chapter 6? All right, I'll answer. What do we have?
Okay, how can like the bonds be polar, but then the whole thing be non-polar?
Oh, it's a great question. That's a great question. Let me pass out to, I'll just make another copy of this. You are gonna have, for your homework, we told you, we just wrote these down, which ones they were. You're gonna have this table for electronegativities on the test. This is the periodic table you have in front of you for the test. Does anyone see Miss Stitzline at all? I need to get her, I'll have to take one in the office, have them send her one of these. So this is the periodic table we have. And she asked a great question. How can we have a polar covalent bond on a nonpolar molecule? I use natural gas as my go-to. So let's take a look at this. When I ask this question, I have you draw a Lewis structure. So technically, am I right? If we have CH4, don't we have carbon? 1 times 4 is 4. Hydrogen, 4 times 1 is 4. We have a total of 8. We add now this next step, this is our skeleton structure. We add unshared pairs of electrons to satisfy the octet rule. I won't say who did this, but I've seen someone start doing. Question, hydrogen, how many electrons does it want in its outer shell? 2. So on hydrogen, we don't add unshared pairs of electrons because hydrogen doesn't follow that octet rule, it follows the duet rule. It wants to get 2 in its outer shell, it gets a really tiny atom and become like helium. Okay? So there it is. Now in the discussion, is this, what type of bond is that right there? Covalent bond, sharing how many electrons? 2, it's a single bond. So that counts as 2 electrons. So we have 2, 4, 6, 8. Now I have a question. What type of covalent bond? How did we do that? We looked up on a periodic table, look at carbon, it's a 2.5. Its ability to attract electrons. Isn't that what electronegativity is? A measure of the ability of an atom to attract electrons to itself in a chemical bond. It's bonded. It's a 2.5 in tug of war with a 2.1. We get 0.4, which puts us slightly into the polar. So, would everyone agree that this is partially positive and this carbon's partially negative? And this is partially positive and partially negative. And this is partially positive and partially negative. And this is partially positive and partially negative. So is that a polar? So I've had people say, yeah, well that's a polar molecule. Is it? everyone agree that it is partially positive all the way around? Can I draw a line through it and say, aha, the partially positive end and the partially negative? I can't. So as a result, when it bumps into another methane molecule, they are not attracted to one another. They don't cling together. They don't form any hydrogen bonds.
So
Okay.
if you.
Technically, no, listen, I brought liquid nitrogen in and we can liquefy it. We can cool it down. And if we cool this down enough, eventually it would form some bonds and start clinging together. It will liquefy. But as it is right now, we're saying that is not a polar molecule.
So if you did draw a line through it and it had like a, negative and it, positive sign, then it would be a polar molecule?
Then it would be a polar molecule. Let's do this, watch this. There's that. I like to put the molar masses. So that is at 16 grams per mole. It is lighter than water even, okay? Let's do this. Let's turn to methanol, okay? We now have an oxygen, correct? One oxygen times 6 is 6. Aren't we at 14? Let's add unshared pairs of electrons to satisfy the octet rule. 2, 4, 6, 8, 10, 12, 14. There it is. Now can you see that, man, I can draw a line through this and I don't have equal halves, do I? I'm still partially positive, partially positive, partially positive. So wouldn't this end be the partially positive end? And look here, what is that? There's 2 electrons. Are they shared? 2 unshared electrons on a strongly electronegative atom. I have a definition I kind of need you to know, but I'm not going to ask. Remember talking about hydrogen bonding. Hydrogen bonding is an intermolecular attraction. So I've had people say, that's a hydrogen bond. That's not a hydrogen bond. That's a polar covalent bond. Here's a hydrogen bond. If another one of these molecules comes along, or even water. Water and alcohol can mix. Let's not do that. Let's say another one of these molecules comes along, and if this is the partially positive end, and this is the partially negative end, would you agree that there's going to be an attraction, a hydrogen bond? Watch this. Hydrogen bond is an attraction between a hydrogen, it's an intermolecular attraction between a hydrogen that's bonded to a strongly electronegative element, that carbon, and an unshared pair of electrons on another strongly electronegative element. But isn't that kind of complicated definition? What's it really? It's really the positive end of one molecule being attracted to the negative end of another molecule. Isn't that a better way of looking at it? So I'm going to have you, when I talk about hydrogen bonding, I'm going to have you illustrate it and define it. It's just pretty easy to illustrate. Because I know the positive end is going to be attracted to the negative end. They'll cling together, they'll be a liquid.
How do you know which side is positive and which one's negative?
What's the charge on electrons? Negative. Yep.
Wait, so I thought that for the polar and non-polar we use the electronegativity numbers, yeah. But then for the first one, when you showed it, it was polar, but then you said it's actually non-polar.
You're exactly right. That's a polar bond, but yet the molecule's not polar because there aren't any electrons out there.
Okay.
Do you understand? That's a good question. She's like, isn't that, yes, those are polar bonds, but the molecule's not polar.
Why? Why is it not polar?
Because I can't see one side being different than the other.
So only if there's electrons it's non-polar?
They do. only if there's electrons somewhere are you gonna, no, watch this, don't, no, I don't wanna answer, I don't wanna ask, because watch this. Carbon tetrafluoride. Carbon, 1 times 4 is 4, fluorine, 4 times 7 is 28, a total of 32 electrons, there it is. A 2.5 in tug of war with a 4.0. 2.5 versus a 4.0. Is that 1.5? Polar covalent. So those are all polar bonds. 1.5 is a pretty big polar, heading towards ionic. Is that a polar molecule? We've got electrons now. Would you agree that it's the same? It's slightly positive in the center, slightly negative all the way around the outside. That thing, I cannot draw a line through it and say, I've got a partially negative side of that and a partially positive side of that. So it is not a polar molecule. And that's what that one question that Emma asked about that bond, what was that, question number 10? Question number 10. It was, you're looking at the whole thing to decide whether it is a polar,
So the carbon, like with the hydrogens, there's no electrons. Like, how do you know which one's positive, negative, or?
because of the tug, who's winning the tug of war. So watch this. The fluorine's the perfect 4.0 versus a 2.5. In the sharing of these two, can everyone see that that line is 2 electrons being shared? Can you agree that it's almost stealing it? Let's move it closer to the fluorine. It almost steals it, but not quite. They share it. Does that make sense? Making that almost a -1 charge. Fluorine wants to be a -1 charge.
What does it?
In the very next chapter, we're gonna assign oxidation numbers. So we're gonna take a look at even covalent. First off, overall, just general, would everyone agree that ionic exchanges electrons and polar and non-polar covalent share electrons? In the next chapter, we start assigning what's called an oxidation number. And it's just a fancy way of saying what's the charge. Even though this hasn't stolen them, we still are gonna say that in carbon tetrafluoride, carbon gets its -1 charge, because it doesn't share with anyone. It didn't completely steal them. As a result, if there's 4 -1s, what's the charge on carbon? A +4. So in this situation, carbon's a +4 because there are 4 -1s. There's only 1 carbon that has to be, but that's down the road. Don't worry, but that's where we're heading. And they're just looking at that tug of war, and they're saying who wins that tug of war as they do it.
What if it was like one that had like only like 3 places to bond? Like if it was like carbon going in the middle, but like okay, but it wasn't carbon, but it had like a double bond somewhere. Like
No, okay, I see what you're saying. You're talking like talking like ammonia? There's only 3 places to bond? It's good. It ends up being more like this. She's exactly right. Ammonia gas is definitely a polar molecule. We have a 3.0 versus a 2.1. What is that, 0.9? So those are polar covalent bonds. And would you agree, we can definitely draw a line through that and say the partially negative end, the partially positive end. That stuff's crazy dangerous. That's the stuff that would attack water. And those electrons have such a strong pull, it pull an electron away from, or hydrogen away from water.
So those numbers up there, they're kind of useless. You just look at because if you look at the skeleton, then you can tell by.
That's what I'm saying, but like, basically, so you're saying there's a question on the test that's like, is that molecule polar or non-polar? The molecule itself is non-polar, but the bond is polar?
Yes.
Okay.
Yeah. So in essence, when you're looking at the molecule, what she's saying, you can almost ignore who's winning the tug of war, just look at that, not even knowing anything about any tug of war. Can I draw a line through that? That's what you're saying? Can I draw a line through that and say one side's more negative or more positive? You can't.
Are you gonna ask about just like if the bond is polar or non-polar, or just?
Yeah. I'm gonna ask, discuss why some things are solids, some things are liquids, some things are gases. So watch this, what did I use? Rebecca, what did I use the other day?
I don't know what it's called, but like, you had a gas, it's like 4 C's in the middle and then hydrogen's all around, like carbon's in the middle. I don't know what that is. And you said, like it bounces off the non-polar molecules, that's how you know it's a gas, because it's bouncing off.
So let's do this. Sodium chloride is 58 grams per mole. Okay? Butane is 58 grams per mole. So they're the exact same. This, sodium chloride, would everyone agree, is a solid. This is a gas. And let me do another one here. If I did isopropyl alcohol, would everyone agree that that's 36 and 16 is 52, you're at 60. And that's a liquid. So I have three things. They're really close to being the exact same mass. One of them's a gas, one of them's a solid, one of them's a liquid. Could we explain why? If I've done my math right on this, 12 times 3 is 36, and 8 is 44, and 16, 44, and 6, it's at the 50, we're at 60. We're 60 grams per mole. I just stumbled on a really good problem. Why? You're gonna have to draw Lewis structures. I'll say draw Lewis structures and explain why the one's a liquid, the one's a solid, and the one's a gas. I can tell you this, watch this, I want to show you one thing right now. When you show this one, sodium chloride, what's the charge? First off, what type of bond? Ionic. Ionic bonds are solids. Here's why, watch this. When you say ionic, what happens? It exchanges electrons. We actually have a +1 charge bonded to a -1 charge. It completely stole this electron. They're not sharing anything. They've exchanged electrons. As a result, remember we showed that cleavage in that sodium chloride the other day? So we have a +1 and a -1, and we have chlorine with a -1, and sodium with a +1. They're just locked in. They're a solid. Do you understand that? Because they've exchanged those electrons. All right? Ionic bonds are going to be solid.
Always.
They're locked in. Completely positive end, completely negative end, they're held locked in place into a crystal structure. Does that make sense? Now, let's deal with the liquid and the gas. Let's draw Lewis structures. I'll give you a little bit of time. Draw your Lewis structures, see if you can see it. I think you will. I think you will. If not, it's good practice drawing Lewis structures. Yeah, we're getting to some deep, a little bit deep water here. Anytime it's qualitative analysis, describing what's going on is always hard.
Wait, is that number by the carbon, is that a 7 or 4?
That's a 4,
Oh.
C4. C4H10, C3H8O. Oh, can we just do this? This one's heavier than this one, so that's why this one's a liquid and this one's a gas. Don't do it. Don't do it, or I'll throw radon at you. What's radon, 222? 222. Is that heavy enough for you? The thing's a gas. That thing's a gas. Why is, real quick, let's look at this. There's radon. Why is it a gas? How many atoms outer shell? 8 electrons in its outer shell. It has need of nothing. It's not gonna bond with anything, it's a gas. Okay. I think just to answer my own question. That's my gas. Miss Carol, why is that thing gas?
Because it'll bounce off because there's a thing to connect to it.
Why does it bounce everything to connect? Why won't it attract anything?
Non-polar molecule.
It's a non-polar molecule. Can you see that there's no positive or negative end? Now I've got to warn you, if we get a little bit bigger, so that's butane, pentane's still a gas. If we get to hexane and septane and octane, everyone knows, does everyone ever have gasoline on their hands? We were like painting and washed off our hands with gasoline.
Yeah.
You ever feel how it feels really cool because it evaporates real quickly? So it is a liquid because it's a bigger molecule. Eventually, you slow those down enough by making them bigger, they will become liquids. But that right there is a gas.
Wait, can you say again why a gas is gas? Why is a gas a gas?
Because it's a not, even though each one of them, even though that is a polar bond, I can't draw a line through that and say, well, this side's more positive and this side's more negative. Watch what I can do with the rubbing alcohol.
So we can say all non-polar molecules are gases.
You can't really say that, because I just said if we get bigger, but this non-polar molecule is a gas. I told you that's a gas.
But like on the test, if we explain it that way, like is that?
You can just explain that it does have a positive or negative end to attract one another. So as a result, it's gonna be a gas. This is gonna become clear, I think. Watch this one. It's 12. Hydrogen, 8 times 1 is 8. Oxygen, 1 times 6 is 6. Are you agree we're 26?
Yeah.
That's kind of odd. 26 as well. All right, here we go. If you make a chain of carbon, technically this is propanol. If I wanted isopropyl, I'd bond this oxygen to the center carbon, but it still doesn't matter. Okay? Add unshared pairs of electrons to satisfy the octet rule. Here we are. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 electrons. Would you agree that we can now draw a line through this? And we've said all those hydrogens are kind of partially positive, correct? So that's a partially positive, and a partially positive, and a partially positive. Can you see that electron and that electron? Without a doubt, those are negative because they're electrons. again, I'm not gonna ask you the definition for a hydrogen bond, but there's gonna be an intermolecular attraction, which in this situation is actually a hydrogen bond. It is between, watch this. Let's do something real quick. You see the water? Does rubbing alcohol and water mix together? Does rubbing alcohol and water mix together? Rubbing alcohol is mainly water. They just put a certain percentage of alcohol in that. Okay. So in this situation, watch this. Would you agree that this hydrogen bonded to a strongly electronegative atom is attracted to unshared pairs of electrons on another highly electronegative atom? There it is. Or another one of these. Draw the same exact molecule, watch this. Carbon, 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 oxygen. That attraction is a hydrogen bond. We have a polar molecule. As a result, they cling together. Who never thought it was so complicated just to figure out why something's a liquid, why something's a gas? But that's what it is. There's where we're at. Do we have any more questions over the homework or the quiz? Yes.
Wait, so basically, is it like all non-polars are gonna be gas, and then all polar molecules are gonna be liquids, and all ionic bonds are gonna be solids?
No. You can't sandwich me into that. Because eventually, watch this, eventually, you get a big enough chain of hydrogen and carbon, it's just too big to be a gas. Because it moves slower. Can we introduce London dispersion force right now?
We already did.
Let's talk it again. Eventually, if I slow particles down enough, they will cling together. And the only explanation for that is the London dispersion force. London dispersion force is I'm going to use a really easy one. I think that's maybe the easiest to show it. Would everyone agree that hydrogen gas is H2? Draw the Lewis structure for hydrogen gas. Agreed? 2 times 1 electron is 2. That's it. Did everyone agree that let me redraw that. Isn't that really 2 electrons being shared? 1 from each hydrogen. Would everyone agree that's a perfect tug of war? Would everyone agree that hydrogen is really, really light? This thing's going to be a gas forever, right? We could never make it a liquid. Can we make it a liquid? If we cool it down to it's really, really cold, it becomes a liquid. How's that possible? Here's London dispersion force. London dispersion force says that as these electrons fly around in here, there's a point in time which the 2 electrons are closer to this hydrogen, making this part partially negative and this half partially positive. I can now draw a line through it and I've got a polar molecule. But it's a very small force. When another polar molecule, watch this, when another molecule comes along, and during that split instant, it has more electrons on this side, making a partially positive and a partially negative, won't the partially positive end of this one be attracted to the partially negative end of that one? London dispersion force. There it is. Does that make this a liquid at room temperature? Oh, no, not even close. We have to cool this thing, we're approaching absolute zero when we get this to finally become a liquid. Does everyone understand that? It's light, it doesn't wanna be a liquid. So as a result, we have to really, really, really slow it down. Slows it down. And eventually, those, London dispersion force is large enough to make it liquefy. Everyone understand that? I used the football analogy. Gas molecules are moving at 1,000 miles per hour. When they collide with one another, they're not gonna cling together, they're bouncing apart. However, if you took a shower this morning in a cold bathroom, anyone take a shower this morning in a cold bathroom? Did you fog up the mirror? Did you have fog in the bathroom when you got out? What happened? That was a stronger force than London dispersion force. It was hydrogen bond, making those water molecules cling together, making it become a liquid. Okay? Back to your question. That's London dispersion force. If I slow the molecules down, eventually that will make them liquefy.
Okay, so besides that,
If I make this chain big enough, I'll slow those particles down at room temperature. You understand?
Yeah.
Because the bigger molecule, so that's butane. If I go to 5 carbons, now let's do this. 5 times 12, so you are at C5H12. 5 times 12 is 60, we're at 72. So at 72 grams per mole, we're still a gas. Hexane is now a liquid. Very volatile, evaporates very easily. Hexane, we're now at 6, you're at 72, C6H14, right? 72, what are you, about 86? At about 86 grams per mole, we have a big enough molecule moving slow enough that it becomes a liquid.
So it's like, if it gets over certain.
Eventually, big enough molecules are gonna be liquids, or even
What
solids.
number is it?
It depends. You know what I mean? We're dipping our toe into organic. You don't want certain, I'm not gonna ask you that. Do you understand? I'm not gonna, and I will tell you whether it's a solid, liquid, or a gas. Yeah. Because, we don't wanna talk much more organic chemistry. It becomes a nightmare. If we get, but watch this, C6 through about C12, H26. That's the range of liquids. We get beyond that, we're talking wax, we're talking our paraffins. And so, anyone's ever played with a wax handle, that is essentially just a bigger chain of hydrogen and carbon.
So what definitions do we need to know? You said we don't,
Everything off that first quiz,
but like on this chapter.
wow, well, you better know, I
Do we
said,
need them to
I said I'm gonna have you draw a picture of hydrogen bonding, illustrate hydrogen bonding. We'll talk about solids, liquids, and gases.
What about the London dispersion force? So we're gonna need to know a definition for it?
I have you illustrate London dispersion force and such and such gas or something. Illustrate hydrogen bonding. I think it probably helps you to know that hydrogen bond is between a hydrogen bond to a strong electronegative and those unshared electrons on another one. It's an intermolecular bond, same as London dispersion force, intermolecular bond. Listen, you'd be amazed, you know how many people I have tell me, illustrate hydrogen bonding. Oh, there it is. It's a hydrogen bonding to a carbon, hydrogen bonding. That is not hydrogen bonding. That is, what type of bond? That is a single bond. It's a covalent bond. It's 2 electrons being shared. Are they shared equally? No, because it's a 2.5 versus a 2.1. So it's a polar covalent bond, because it is 0.4.
Well, we need to know like write out the steps of the Lewis structure, like as long as we know
No,
how to
no,
make
no.
it? Okay.
What
Nope.
about, do you know like metallic form?
I'm not gonna ask for top ones. Those are a little bit weird.
I have a question from our chapter 5 quiz. So, for electron affinity, why is it usually negative?
Why is electron affinity usually negative? What is electron affinity?
The change in energy when an electron is acquired by an atom?
So I had told you a way to cheat a little bit, because those definitions are confusing. One of them you're adding electrons, one of them you're removing electrons, one of them you're tug of warring on electrons. And this confuses a lot of people. Here you're adding electrons, what's the matter? What's so funny?
It's how you, it's how you were like sounding out.
Oh. So, make that a delta. That delta's the only one that's changing energy. And I'll be more picky on this on your test if you have these right.
Yeah, but why?
So don't come back to me and say, we didn't mark it wrong on the quiz, this is on you. I'm gonna be picky that you have these ironed out. Electron affinity, the change in energy when an electron is acquired by a neutral atom. Why is it usually negative? If you have a negative change in energy, you agree that energy is given off or lost. That's what makes it usually negative. Okay? Cation. This is the energy required to remove an electron from an atom of an element. And electronegativity is the measure of the ability of an atom to attract electrons to itself in a chemical bond. You have that on your chart. So I can't even ask you the trends on that one, on the test, because you'd be able to look at the periodic table that you have in front of you and see the trends.
So you're not gonna ask us like.
Well, that's the definition, but I won't ask you trends on that.
Okay.
But you know them anyway, because decrease, increase, all the rest are opposite.
Are you gonna ask,
And that's atomic radius, by the way.
are you gonna ask the polyatomic ion?
Yeah, you need no polyatomic ion. That's really, isn't that the only thing new we introduced this chapter? I think so. We had valence electrons in the last chapter. Are you sure we're not ready? I think we're ready.
Something about weather, what's weather?
All right, listen, then tomorrow, we're gonna give some more notes on weather. No, this is super valuable, it truly is. It truly puts all this together, it's a big picture thing that I think you should know.
Will weather be on the test then?
Oh, it could be, yeah.
So if we don't want it, it won't be on the test?
So, what, no, we're not ready, we're gonna take, I'm gonna give you some notes on weather.
On the weather for tomorrow. Partly cloudy.
So on Monday, Tuesday?
I think another week after.
Might be a
Yeah, which will be tomorrow, we'll finish our review tomorrow.
Wait, why is this?
What if weather takes the whole time?
Listen, if weather takes the whole time, then we maybe will put it on the test, and we will, yeah, that's a good idea.
Wait,
And I'll
why?
give you, we'll go Monday, Tuesday. We'll go Monday,
Wait, and weather will be on the test?
nope,
It's not a good
Monday,
deal.
Tuesday, let's go Monday,
What
Tuesday,
about weather?
and weather's on that now. It's gonna be fantastic.
Elena, you can have it on your test, I don't want it on mine.
No, it's good, we're Monday, Tuesday,
Is it so complicated?
Monday, Tuesday, no.
Is it
Oh, it's gonna be
This is big
complicated.
picture stuff, this is awesome stuff, it really is, you need to know.
What's the most evaporate, the water evaporates?
Water evaporates, listen, do you guys understand that water evaporates?
Yeah.
Do you understand that it condenses and forms clouds?
Yeah.
Do you understand that it rains back to earth by gravity?
Yes.
Beautiful thing, it's a beautiful thing, we'll explain it. We'll explain more of this and how it happens. So we're gonna give some more notes, you guys fire me up. I love the fact that you wanna learn science. That is awesome. That is awesome.
Ruth is giving, what's his name? No, what is that? Bill Nye. Ruth's giving Bill Nye.
I thought it was so awesome. It made me, I knew, they gotta find out.
I just handed this definition. Oh, I got it.
Skip that chapter, just keep it. Give me, I'm not all on. I'm gonna get to bed, so I'm gonna get to bed. You can drop everything else. Oh, yeah. Yeah, covalent bonds, are they sharing or exchanging electrons?
Wait, I thought exchange was
They're
ionic.
sharing.
Let me make flashcards.
Ionic bonds are doing what?
Oh, yeah.
Ionic bonds are doing what?
That's what I'm gonna do next. Exchanging electrons.
Exchanging. Covalent versus non-covalent.
Polar versus non-polar, you mean?
Oh, yeah, polar versus, let's say covalent, non-covalent.
Yeah.
Polar and non-polar.
Polar is unequal sharing, and non-polar is equal sharing.
Yeah. Hey, sit down, guys, sit down, we're not freshmen or junior high kids. We can actually sit in a seat and wait till the bell.
I think I started doing that.
You realize I can't even come back and substitute teaching,
Why?
because I'd lose my mind. I would lose my mind. Cause I'll walk into another classroom,
Yeah.
it just wouldn't work. Just wouldn't work.
I think they listen to you.
No,
They must have one.
they wouldn't know, they wouldn't know. I look like Santa Claus.
You're like a legend, everyone will know.
No.
He's a legend.
Candy bar. Daniel.
Well, what's with the candy bar? You were passing around, they come back in candy bars, they had all the good candy bars. Is
Wait,
it true you have a Snickers bar?
No, I don't have any more. I just have this.
Do you realize that Musketeers are supposed to discriminate against candy
So
bar?
it's really awesome because my mom is the manager of the Parmar store in Apple Valley. So the things that don't sell or put basically in her car and brought home. So I have 2 totes filled with a bunch of candy and chocolate.
oh, bring it in. Yeah,
And
you
then,
can have it.
and then I also have a drawer in our kitchen that about 3 drawers and that's the same thing.
And you can have it, bro.
I most definitely
You're tall and skinny, what's wrong with you?
Why are they selling 3 Musketeers now?
Why are you
No
not?
joke, my mom actually has like the boxes that they put in stores filled with them.
Remember Miss Shaw?
There's like 30 in one box.
Okay. Did you ever show?
I know, right?
Yeah. Anybody? Yeah, she would bring in like the candy her husband would sell. Remember that?
So, why do bring candy for your chemistry class?
Wait, Mr. Weber, you know what we should do with the candy bars that he brings in is do the like freezing. Dry, like freeze dry it.
That's good, that's a good idea. A good idea.
My birthday's in delay at 4 months. I don't think
Someone wants turned off the camera, we're done. I don't know how to do it.